Hello friends. So today we are going to discuss electromagnetic induction, which is one of the basic principles in electrical engineering. So what is electromagnetic induction? Electromagnetic means relating to interrelation of electric currents and magnetic fields, and whereas induction means process of bringing about or giving rise to something. With respect to electrical engineering, electromagnetic induction means the production of voltage or electromotive force due to change in magnetic field. So, Michael Faraday in 1831 discovered the phenomenon of electromagnetic induction. Further, he stated two laws of electromagnetic induction. So now we will discuss first law of electromagnetic induction. As per Faraday, whenever there is change in magnetic field experienced by coil or conductor, EMF gets induced in that coil or conductor. On same basis, he also stated second law, and as per second law of Faraday, the magnitude of induced EMF is proportional to rate of change of flux, that is E is proportional to d phi by dt, where phi is flux. Now if you are having a coil of n number of turns, then what happens is this coil of n number of turns, when it experiences change in flux, then by simple formula, the magnitude of induced EMF can be given as E is equal to N d phi by dt. Unit of EMF induced is volt. So now if you see a simple experiment, if you perform, if you are having a piece of magnet and a coil, and if you move the magnet with respect to coil, then coil experiences change in flux. This change in flux induces EMF in the coil that can be sensed by galvanometer. So now we need to understand what are different types of induced EMFs. Basic two types of induced EMFs are statically induced EMF and dynamically induced EMF. Statically induced EMF is further classified into self-induction and mutual induction. Now we will understand what is meaning of dynamically induced EMF. So whenever there is relative motion between magnet and a coil, that is, whenever the process of motion or dynamics is involved and that is leading to EMF induction, then it is called as dynamically induced EMF. For example, EMF induced in generators, dynamo, etc. All of us have sometimes used dynamo in our bicycles. So when inside dynamo, as wheel of the bicycle rotates, dynamo rotor also rotates. Inside it is having a magnet, and hence the coils inside the stator of the dynamo experience change in flux and EMF gets induced. This induced EMF we use for lighting the lamps on a bicycle. Mathematically, dynamically induced EMF is given as E is equal to BLV sine theta, where B is magnetic flux density, L is active length of conductor. That means active length means the length which actually experiencing change in flux. V is velocity with which conductor is moving, and theta is angle made by conductor with respect to magnetic field. So based on this, every single generator in thermal power plant is working on same principle. The only thing is we are having large number of coils, large number of turns of coils, huge amount of magnetic flux density in order to produce voltages in the range of 11,000 to 15,000 kilovolts. Now, moving forward, let's understand what is statically induced EMF. Now, as shown in the figure, if you are having a variable resistance connected in series with a coil and a source of voltage, and if you vary the amount of resistance, the current flowing through coil will vary. Now, this variable current will lead to production of variable magnetic field, as stated by Oersted. Whenever current flows through coil, it produces magnetic field, and hence this variable magnetic field will link with coil itself, leading to EMF induction by Faraday's first law. So whenever change in coil leads to EMF induction in coil itself, it is termed as self-induced EMF. For example, EMF induction in electromagnetic ballast, choke in fluorescent tube circuit. Mathematically, self-induced EMF is given by E is equal to L di by dt, where L is coefficient of self-induction or inductance of coil. Self-inductance is defined as property of coil which tries to keep current constant. Inductance is measured in Henry and it is given by N phi divided by I. Di by dt is rate of change of current. So, statically induced EMF will have higher magnitude if there is higher value of inductance and higher value of rate of change of current. Second type of statically induced EMF is mutually induced EMF. Now, if you see in this figure, we are having two coils where coil A is supplied with a source of voltage and in series it is having a variable resistance. Coil B is placed nearby coil A. Now, if we vary the resistance in coil A, it will lead to change in current in coil A and hence change in flux produced by coil A. This change in flux produced by coil A also affect the flux which is linking with coil B, and hence in this case actual change in current is in coil A but EMF will get induced in coil B and hence it is called as mutually induced EMF. So you can define mutually induced EMF as whenever change in current in one coil leads to EMF induction in the other coil. For example, if you see a transformer primary is supplied with sinusoidal voltage and actually EMF induction takes place in transformer secondary. So change in current is in primary winding of the transformer whereas EMF is getting induced in the secondary coil of the transformer. So this is what is mutual induction. Mathematically, mutually induced EMF is given by E is equal to mdi1 by dt or E is equal to mdi2 by dt. Here there is minor correction, here it should be mutually induced EMF. Now, as you can see, these are two equations. There are two equations because there are two independent coils involved in this. If you are applying source of voltage to coil 1, then this first equation is valid, that is E is equal to mdi1 by dt, and that is leading to EMF induction in coil 2. But if your source of voltage is given to coil 2 and it is leading to EMF induction in coil 1, then this equation, that is second equation, E is equal to mdi2 by dt holds true, where M is called as mutual inductance of coil and it is measured in Henry. So M will also have two equations depending on to which coil you are providing supply. If you are providing supply to coil 1, then M is N2 phi 2 upon I1. If source of supply is given to coil 2, then M is N1 phi 1 upon I2. And hence, dynamically induced EMF, there is no motion involved. In case of static induction, there is motion involved, and further, in case of static induction, we are having two types of EMF induction, self-induction and mutual induction. Self and mutual, both induction depends on the rate of change of current. If rate of change of current is higher, the EMF induced will be higher. Now, we need to understand laws or rules to understand direction of induced EMF. First and basic law, as all of us know, is Lenz's law. As per Lenz's law, induced EMF always opposes cause responsible for its production. So mathematically, Lenz's law is completely opposite to that of Faraday's second law. As per Faraday's second law, equation is E is equal to n d phi by dt. So as per Lenz's law, equation is same, only there is minus sign added to RHS. So as per Lenz's law, E is equal to minus n d phi by dt. Second law or rule to understand the direction of induced EMF is Fleming's right hand rule. As per Fleming's right hand rule, as you can see in the figure, if first finger is indicating direction of magnetic field and if you move conductor in the direction of magnetic field, motion of conductor is given by thumb, then middle finger indicates direction of induced EMF. So as per right hand rule, Fleming's right hand rule, it is applicable to motor, and we already know Fleming's left hand rule is applicable to motor, and right hand rule is applicable to generator. So these are two laws or rules to understand direction of induced EMF. First is the Lenz's law, by which E is equal to minus n d phi by dt, that is, induced EMF always opposes cause responsible for its production. And second is Fleming's right hand rule, which is applicable to generator, wherein if you move a conductor in a magnetic field, EMF gets induced. So first finger indicates direction of magnetic field, thumb indicates direction of motion of conductor, and induced EMF is indicated by middle finger. Now, after going through this video, I request you to do these activities that will help you to solve examples. Please pause the video, note down these questions, and try to solve. All the three questions are based on three basic equations which we have understood in this video. I hope you're liking my videos. I request you to please subscribe and share these videos to all the learners so that they will get benefited. Also, I'd like to tell you, or you may come across some queries. You can add some critics or comments below this video and help me to improve my videos further. Thank you very much. Thank you.